Let's look at a dryer load calculation. What is the total VA load you would calculate for one dryer with a nameplate rating of 4,500 VAs in a residential home? I want to note that every piece of equipment should have a nameplate on it stating its voltage, amperage, and or wattage. Sometimes it'll have horsepower or different things like that. So if you want to check a microwave or a dishwasher or a motor, should have a nameplate on it stating some of this information. We flip straight to our calculations tab in our code book and head to Article 220. We see that this is about calculations and it doesn't mention anything specific, so we just head to Article 220, which is our calculations tab. We look at the black bold headings for dryers. I want you to look now. You know you're in the right article. I want you to look at the black bold headings until you find something about dryers. Pause the video now if you need to. We find that in 220.54 that dryers shall be calculated at either 5,000 VAs or at the nameplate rating, whichever is larger. So it's a 5,000 minimum or the nameplate rating, whichever is larger, and you'll use that for your load calculation. Okay, always reread your question and then carefully make sure that you use the correct process and select your answer. So many questions have I went back through. Often your testing center will allow you to mark a question. So if you feel like you didn't get it right or you want to spend a few more minutes on it at the end, you can mark that question. Many times have I went back to a marked answer and I knew the answer and I had just clicked the wrong button. So you always want to go back through your answers and make sure that you click the right answer. So it's very important. How many VAs would you calculate for a 9 kVA range in a single-family dwelling unit in Chicago, Illinois? We flip straight to our Calculations tab in Article 220. Then we're going to read our black bold headings until we find something about ranges. I want you to pause the video now if you need to and flip through Article 220 and look at the black bold headings until you find something about ranges. We find Article 220.55. Go ahead and read it now. Pause the video and read it all. Let's flip there and now let's look at the table that it said that we could look at. Table 220.55. It's on the next page. Okay, let's take a second to look at table 220.55. On the left-hand side, you'll notice it says number of appliances. This is going to be the number of appliances that are listed in your load calculation. Column A is going to deal with appliances that are 3.5 kW or less. Column B are going to be 3.5 up to 8.75, and column C is going to be from 8.75 but not over 12. I want to point out that column A and B are demand factors. So you would take one range, multiply it if it was, say it was 5 kW. This table is saying that you would apply an 80% demand factor. You would use column B and you would use one appliance. So you would use one appliance, slide over to column B and multiply it by 0.80. In our case, our range falls into column C. It's asking for a 9 kVA range. So column C is a little different. It is not demand factors. It is a fixed kW rating. So any range that falls in between 8.75 and 12 is going to be 8 for 1, 11 for 2, 14 for 3, 17 for 4. That is the fixed load that you will have for your calculation. Okay, so ours is greater than 8.75 but not over 12. We're going to use column C. We use the left-hand side to select our number of appliances. Then we slide over to column C and we're going to use 8 kVA for our load calculation. We select C. How many VAs would you calculate for a 14.6 kVA range in a single-family dwelling unit in Asheville, North Carolina? So we've got some options. We flip straight to our Calculations tab in Article 220. Table 220.55 states that ranges over 12 kVA through 27 kVA of the same rating, the kVA rating in column C shall be increased by 5% for each additional kW of rating or fraction thereof. Now this sounds confusing, but you can do this. We're going to show you how. Another thing I want to mention, the only way you're going to get good at dryer calculations, range, any calculation is through repetition and practice. So let's show you how to do this the first time. Okay, so first you have to find out how many kVA you are past 12. It's saying that you must increase it for each kVA past 12, 5%. The code states that it's a kVA or major fraction thereof, just like in multi-outlet assemblies. So if it's past if it's 0.5 or past, it's going to count as another kVA. 14.6 is going to be the same as 3 because the 0.6 would be rounded up. So we are 3 kVA past 12. So for each one past 12, we're going to increase that column's number by 5%. We're dealing with one range, so the kVA for that column is 8 kVA. Now we need to increase 8 by a 5% multiplier for each kVA that is above 12. 3 sections is going to bring it up by a 15% multiplier. 5 for each section. So just take 8 and multiply it by 1.15, and that is going to give you 9.2. I want to note that if you want to increase any number by a percentage, we will just multiply it first by putting a 1 in front of it and then whatever the percentage is. In this case, we want to increase it by 15%. So we just take 8 multiplied by 1.15, and that is going to give us 9.2 kVA. How many VAs would you calculate for a 15.6 kVA range in a single-family dwelling unit in Asheville, North Carolina? We flip straight to our Calculations tab in Article 220. Table 220.55 states that ranges 12 kVA through 27 of the same rating shall be increased by 5%. We have 15.6 kVA, so we're going to be 4 kVA beyond 12 because we're going to round that 0.6 up. 4 multiplied by 5% equals 20%. Now we go back to column C to check what we are increasing. In this case, it's one range. So in column C, one range is good for 8 kVA. Then we just increase it by multiplying 8 by 1.20. That's going to give us 9.6 kVA. And we're going to select D. What is the calculated neutral load for a 1,500 square foot home with an 1,100 watt dishwasher, a 9 kW range, a 35 watt water heater, and a 5 kW dryer on a 122/40 volt service? I'm putting in here that the loads are calculated using the standard method. Okay, so first we're going to figure out our VAs per square foot. We've learned this already. This is our basic load calculation. If you are catching this in the middle, I have an entire 10-week free course that teaches you how to do all the things leading up to this. It's absolutely free. Would love for you to check it out. So we have 1,500 square foot.
multiplied by 3 VAs per square foot. That's going to give us 4,500 square foot VAs. Now we have to remember our small appliance and laundry circuits. So that's going to be 2 small appliance and 1 large laundry circuit. Both of those are calculated at 1,500 each. That's going to give us 4,500 VAs for those. That's going to give us 9,000 VAs. Now we need to do our demand factors for the first portion of our load calculation. So step 1, we have the first 3,000 at 100%. Step 2, we do the next 301 up to 120,000 at 35%, which is going to allow you to do another 117,000 total at this 35%. And then step 3, we're going to add those back together. Okay, so we take 9,000 for step 1. We're going to minus the 3,000 that we need to do at 100%. That's going to give us 6,000. Now we take that remaining 6,000, we're going to multiply that by 0.35, and that's going to give us 2,100 VAs. Now we need to add those back together. We take 3,000 and we add 2,100, and that's going to give us 5,100 total general square foot and small appliance laundry circuit VAs for this load calculation. Okay, so we have our general VAs. No timing on this whatsoever. Let's do a bank and office receptacle load calculation. What is the total VA load you would calculate for a 25,000 square foot office building with 250 receptacles? And we're talking about the yokes. Okay, so we've got some options here. Nothing stands out right away. This week, we're going to be relying on some of what we learned last week. And like I said, we're going to take this first one slow and then make some assumptions that we've caught up to this point. So who remembers what the VA per yoke was for commercial receptacles? Right, 180 VAs. Who remembers what code article that was from? 220.14i. We find that in 220.14i that each receptacle is calculated at 180 VAs per receptacle. But what else does it say? Go ahead and take a minute and read it now. Pause the video if you need to. Let's go ahead and flip to 220.14k for banks and office buildings. It's going to be on the next page from what you just read and the top part of the page. So it states that we must use the larger of 1 or 2. So it says the calculated load from 220.14i, which is going to be 180 VAs per yoke, or 1 VA per square foot. Let's learn how to do that now. So first we have to calculate the totals of both. So we take 250 receptacles multiplied by 180, and that is going to give us 45,000 VAs. Then also we take the 25,000 square foot, multiply it by 1 VA per square foot, and that is going to give us 25,000 VAs. But we cannot stop there. This is where demand factors come in. Is this office building going to be using all of its receptacles at the same time? No. Let's check out 220.44. I want you to take a minute and we're going to read it and then we're going to check out its table. It states that the receptacles that are in 220.14i and h, you apply these demand factors. So 220.14k for banks and offices told us that we must calculate it according to I, which is going to allow us to use this code article here in this table and these demand factors. We're going to learn how to do that now. Using table 220.44. So I'm going to show you the easiest way how to apply demand factors no matter what. This table is saying, if you look at the table, study the table, it's saying that we must do the first 10,000 VAs at 100%. Then we must calculate anything over 10,000 VAs at 50% of the value of that. Then you take the first 10,000 and add it back to the reduced load for your total VAs. And I'm going to teach you the easiest way to do that now.
Okay, so that was our total VAs. Okay, so our total VAs. So in step 1, you take your total VAs and you're going to minus the 10,000 that you must calculate at 100%. Then you're going to take that remaining value and multiply it by the demand factor. So 0.50. That is going to give you 17,500. So in step 1, we just took the total. We have to calculate the first 10,000 at 100%, so we have to set it to the side. So we take the total minus the 10,000 that we have to set to the side. That is going to give us the 35,000 remaining. Now we must multiply that by 0.50, the demand factor, and that is going to give us 17,500. Now in step 3, all we do is take the 10,000 that we set to the side, add it back to the reduced load with the demand factor, and that is going to give us the new total VAs. In this case, it's 27,500 VAs. Okay, so now we must select the larger of 1 or 2. These were our original figures. Then we applied the demand factors. Now we must omit the smaller and select the larger, and in this case, it's going to be B, 27,500. Let's do another one. What is the total VA load you would calculate for a 28,000 square foot bank with 230 receptacle yokes? Okay, so we flip straight to our calculations tab in our codebook. We know that we're dealing with receptacle loads inside of a bank. We're going to select the larger of the two, either 1 or 2, 180 VA per receptacle yoke or 1 VA per square foot. Okay, so let's go ahead and multiply our square foot. We have 28,000 square foot multiplied by 1 VA per square foot. That's going to give us 28,000. Now let's take our receptacles. We have 230 multiplied by 180. That is going to give us 41,400. Now, every time you get your total load, you have to check for demand factors. Yes, in this case, the demand factors in 220.44 do apply. Okay, so step 1, we take our 41,400 and we're going to minus the 10,000. That's going to set it aside. That is going to leave us with 31,400. Then all we have to do is take our remaining balance, multiply it by the demand factor, which is 0.50. That is going to be equal to 15,700. Then we just add back the 10,000 that we set aside, and that is going to give us 25,700 total VAs. Now we have to select the larger of the two. In this case, we're going to omit the smaller, which is the receptacle load, and we're going to select the larger, which is the square foot load. And we select D. Okay, let's do a hospital general lighting load calculation. What is the VA lighting demand for a 110,000 square foot hospital? Okay, so we have some options. Nothing really stands out right away. First, we're going to flip to our calculations tab on our codebook. We know that we're dealing with lighting in a hospital. First, we need to find out how many VAs per square foot it is. We notice that in table 220.12, it deals with minimum lighting VAs per square foot. We find hospitals in the table, and it tells us to calculate 2 VAs per square foot. We take 110,000, multiply it by 2 VAs per square foot. That is going to give us 220,000 VAs. Are there any lighting demand factors? Let's check out table 220.42. Let's take a look at table 220.42. On the left-hand side, it is going to list the type of occupancy, the lighting VA load is in the middle, and then the demand factor is over to the right. Do you notice hospitals listed in the occupancies? We do, so we can apply these demand factors. It lets us know that the first 50,000 VAs are going to be calculated at 40%, and the remainder over 50,000 are going to be set up at 20%. So we have to be careful that we're going to structure this question a little bit differently because there are multiple demand factors. So when you're doing multiple demand factors, this method works every single time. So first, you list your total VAs, and then you go ahead and set up your math problem. You're going to minus the 50,000 and then set it up to give you your other total. And you'll see how I've set it up there. Then going across, you multiply the first number by its demand factor. In this case, 40%, it'll be 0.40. That is going to give us 20,000 VAs. Then the remainder, you're going to multiply by 0.20, and that is going to give you 34,000 VAs. You add them together, you have 54,000 VAs, and you select D. What is the total VA lighting demand for a 4,000 square foot storefront in Johnson City with 40 linear foot of show window lighting? We flip open our calculations tab. We know that we're dealing with lighting demands. First, let's figure our VAs per square foot. Table 220.12 tells us that stores are calculated at 3 VAs per square foot. So first, let's calculate the square foot VAs. You take 4,000, multiply by 3, and you get 12,000 VAs. Now let's add it together with the show window lighting VA load. We take a look at 220.14G, and it says that show windows are calculated at 200 VAs per linear foot. So we take 40 multiplied by 200, and that is going to give us 8,000 VAs of show window lighting. Okay, so we have 12,000 square foot VAs, 8,000 of show window lighting VAs. Now let's see if there are any demand factors that we can apply. Let's head to table 220.42. So we look through the types of occupancies. Do you see anything about stores? No. So we just take that total. There are no demand factor lightings for stores. And we select 20,000 VAs. What is the minimum AWG size feeder tap conductor allowed on a 10-foot tap with a circuit that leaves the enclosure with 3-aught copper conductors on a 200 amp main overcurrent device terminating to 75° C terminals? So there's a lot going on here. Let's use our keyword index process and break it down. So let's try F for feeder tap conductors. If you look at the overall theme of this question, it's asking about feeder tap conductors. It's asking about size, and it's got some different, it's got some different information in there for us that might lead us in the right direction. So, okay, so let's head to F. Let's go ahead and pause the video now. I want you to head to F in the index, and I want you to look for feeder tap conductor. Okay, so when we get to F in the index, we do find feeders. We do not find feeder tap conductor specifically, but now we're in feeders. We feel like we're in the right section. We're on page 838 in the third column. Up at the top, we see feeders. Now let's look down in alphabetical order and see if we can find anything about taps. So we go down through. We skim through till we get to the T. and we do find taps. So we found feeder and taps. So we feel like we're in the right section. Lists a bunch of different articles. Let's just go ahead and go through them in order. First, let's try 240.21b. Remember, keep a piece of paper or your hand in the back of the index just in case you need to flip back. Pause the video now and head to 240.21b. Okay, so when we get over here on page 96, in the bottom left-hand corner, we're going to find 240.21, and then we find B, and it says feeder taps. So I feel like we're in the right section. Let's go ahead and continue to read. Conductors shall be permitted to be tapped without overcurrent protection at the tap to a feeder as specified in 240.21 B1 through 5. Okay, so it's going to talk about a bunch of different type of tap conductors. We're looking now, we need to go through our keyword index process, and we need to look for something that is about 10 feet because, you know, we have to go back to our question. We're trying to find out. Okay, so in this case, allowed on a 10-foot tap with a circuit that leaves the enclosure. So we've got a little bit of information. So we look at the black bold headings until we find something about 10 feet long. All right, so now that we've caught up to this point where you look at our black bold headings, we see that right here in part 1, it's for taps not over 10 foot long. If the length of the tap conductor does not exceed 10 foot and the tap conductors apply with all of the following. So when the code book says all of the following, that means it's got to hit every point. We're going to briefly go over it, and then I'm going to take us down to our section. But if you were going through this for the first time, you might want to read every single one of these sections to the T as you're looking for your answer. So the ampacity of the tap conductor is A, not less than the combined calculated load on the circuit supplied by the tap conductor. So if you know that you're tapping this conductor for a 30 amp motor, regardless of all these other codes, it has to be, the wire has to be sized for the 30 amp motor. So, okay. Part B says not less than the rating of the equipment containing an overcurrent device supplied by the tap conductor. So by the rating of the equipment. 2 says the tap conductor does not extend beyond the switch or panel board. Part 3 says except at the point of the connection to the feeder, the tap conductors are enclosed in a raceway or a switchboard or panel board or control device. And then if part 4 is what we're looking for in our question. For field installations, if the tap conductor leaves the enclosure or vault which it is made, the ampacity of the tap conductor is not less than 1/10 of the rating of the overcurrent device protecting the feeder conductors. Okay, so in this case, we're going to use part 4 because our question states that the conductors leave the enclosure, okay, and it lets us know that it is on a 200 amp main overcurrent device. So in this case, our conductors, regardless of the load, even if you have a 2 amp load, you have to size this thing if it leaves the enclosure at a minimum of 1/10 of the overcurrent device that you're tapping from. So we're going to do some simple math, and this is all going to make sense, and we have one more practice question after this. Okay, so we're going to take our main overcurrent protective device, and we need to divide that by 10, because we have to do at least 1/10 of it. So we're going to divide by 10. That's going to give us 10 equal portions of the 200 amps. So in this case, 20 amps is what we now can size our wire by minimum. So even if you only have a 3 amp load and you know the load, you can do a minimum of 20 amps, and that's what you must size your wire by. Now, we are going to head to our ampacity table using our ampacity tab, and that is table 310.15b16. Go ahead and flip there now. So we use our ampacity tab. We're going to flip to page 150. We're dealing with copper conductors. And we are going to go to the 75 degree C column. And we're going to go down and we're going to size based off of our amperage. And that is going to be a 14 gauge wire in this case.
So for this tap conductor, you are allowed to use a 14 gauge wire being protected on a 200 amp main breaker. So I know it sounds crazy, but this is how tap conductors work. And hold on, we're going to do another question.